So let's continue our discussion of the positive or negative polarity of the transformer voltage by thinking about Lenz's law. And we have two approaches that we can take. And there's four different regions of time that we can consider. And let's first look at them quantitatively. So let's use the math, just like we did at time equals 0. So the first region we'll call region 1. And in this region, we have the sine omega t, so the magnetic flux is positive and increasing. So the sine wave in blue is positive, it's above y equals 0, and it's increasing in this region 1. And so in this region 1, we want to look at the transformer voltage and figure out if it's going to be positive polarity or negative polarity, which direction is the current flowing. So in this region, we can see that cosine is positive throughout this region. And that means that d phi dt is greater than 0. But again, all those leading constants are positive. And we still have that little negative sign hanging out right in front of the n. So that means that the transformer voltage is less than 0 in this region. So throughout this time region, point 2 is at a higher electric potential than point 1, which means the current is flowing from minus to positive, just like this. And that's a negative polarity because it's flowing backwards from minus to positive. Now let's look at region 2. In region 2, let's look at the blue line, the sine omega t. So that means that the magnetic flux is positive in this region, but we can see that that blue sine wave is going down. It's getting smaller and smaller throughout this region. The cosine omega t becomes negative in this region. So we have a negative value of the cosine omega t here. So that means that d phi dt is less than 0. But because of that little leading negative sign, we have a negative in front, and then the cosine value is also negative. So the transformer EMF is going to be greater than 0. This means that the point 1 is at a higher electric potential than point 2. The current is flowing from positive to negative, which means that we have a positive polarity. Now in region 3, let's again look at the blue sine wave. The blue sine wave is, we have now in this region, is negative, and it is getting more and more negative in this region, increasing in the negative direction. The red cosine wave is also negative in this region. So if the value of cosine omega t is negative, and we still have that leading negative sign, this means that d phi dt is less than 0, but the transformer EMF voltage is greater than 0. So point 1 is still at a higher electric potential than point 2. The current flows from positive to negative. So this is a positive polarity. The current is flowing from positive to negative, and the transformer EMF is greater than 0. Now, in the last region, the blue sine wave is negative, but it is getting less negative. It's becoming a smaller negative number over time. The red cosine wave has gone back above y equals 0 and is now a positive value again. So the cosine omega t is positive, so d phi dt is greater than 0. And because of that leading negative sign, the transformer voltage must be less than 0. So now we're back to the same situation that region 1 had. Point 2 is a higher electric potential voltage than point 1. The current flows from the negative to the positive, and this is a negative polarity. So looking at all four of these regions, we can see that the current will change direction in each region. The yellow line being the current, and the current will change direction depending on the polarity. So in region 1 and region 4, we have a negative polarity because the current goes from the negative to the positive transformer voltage as defined based on that right-hand rule due to the surface that we picked. And in 2 and 3, we have the current going from positive to negative, which is a positive polarity, and the current flows from positive to negative transformer EMF as we defined from the DS in previous video.